All right, so today we're gonna continue our discussion of quantization, quantum fields. Last time, what we talked about was we quantized using path integrals. We quantized free bosons, right? And today we're gonna do path integral quantization of free fermions. All right. Hopefully, if you make it to the end of this lecture in time, the remainder, so the next section, next part of the course is going to be about adding interactions. And you will see that the presentation we're going to follow is basically, we'll set the stage for that. And then finally, we'll end the course with two more things. We'll have a discussion of scattering theory S matrices. Hopefully, if we have time, I would like to have an epilogue, which is like a summary of the success of all these quantization methods by discussing OM. For QFT1, I think OM model is a huge success. So hopefully we'll get there. I'm hoping that we'll have at least one lecture on that.
Yeah. What did you mean by interactions?
Interactions like not Gaussian.
Interactions?
Interactions.
Oh, I thought you said interactions. Sorry.
No. Interactions.
Okay.
All right. All right. So what did we go over last time? If there are any questions, just ask. We started by talking about path integrals and how they lead to a reformulation of quantum mechanics. The fundamental object in path integrals was the transition amplitude propagator, right? In the field eigenbasis or position eigenbasis if you're in quantum mechanics. Then we also discussed two more things because it's a reformulation of quantum mechanics. You could use path integrals to derive correlation functions. So the trick is to, of course, comes out of the path integral as we had argued before, correlators that are naturally time ordered. That's just like the structure of path integrals will give you that. The trick is to consider this path integral. The top part looks like the time order correlator of these guys, and then this is just normalization. However, to make sure that you project to, so this path integral will have some boundary condition as at minus infinity or a long time ago here, and then some boundary conditions at very late time. To make sure that you project to the vacuum, the way you do it is this long time ago and long time in the future, capital T, minus capital T and large capital T, you do some sort of a I epsilon shift in time. So you do T times 1 minus I epsilon. And when you take the limit of T going to infinity, it basically projects to the vacuum, right? We discussed that. If there are any questions, now is the time to ask. But one key thing that we observe is that this helps the path integral converge, right? This is just a way of taming the UV, ultraviolet. We also said that path integrals could be used to calculate classical partition functions. All along, we've been saying that this is quantum field theory could be used to capture elegantly the continuum limit of critical systems, right? This is classical physics at finite temperature. And the way you do it, the analog of the propagator over there would be transition matrices, right? Transition matrices. And what you would calculate, what you would like to calculate, in this case, we said that what we would like to calculate is a generating functional. Here, what we calculate is a partition function, right? So generating functional for QFT, partition function for statistical field theory. And what it is just the path integral in Euclidean space-time with Euclidean Lagrangian. So this is T going to minus I tau, okay, with some periodic boundary condition, which is, so this is the Euclidean time direction, and you periodically identify tau with beta H bar. Good. This is partition function trace of e to minus beta H. Any questions about this? statistical field theory and quantum field theory. In both cases, you have fluctuations. In the statistical field theory, fluctuations are thermal fluctuations by temperature. So probability densities, right? There's a probability for spontaneous creation of a pair out of your thermal background, right? And in the vacuum case, you have quantum fluctuations. Good. All right. Oh, another thing that we mentioned is that the fundamental equation, if you view this for quantum mechanics, right, 0 plus 1 dimensional QFT, the fundamental equation that we repackaged as a path integral was the Schrodinger equation, right? So there's a Schrodinger operator that we're calculating. Our propagator is the green function for Schrodinger operator, and after an analytic continuation time with weak rotation, t going to minus I tau, Schrodinger equation up to factors of 1 over h bar becomes the heat equation, and the propagators for heat equation are heat kernels, right? So those are our the analog of our transition matrices. Good. So to go from quantum mechanics to scalar field theory, that's QFT 0 plus 1 and QFT in higher dimensions, your Q hat and P hat coordinates become phi A and pi A, right? We've said that several times by now. And your propagator will still have you're doing a path integral, right? Your propagator is a path integral in from some time t initial to t final with some boundary conditions. Here is a phi minus and phi plus. These are field configurations at the initial time and late time. And you're path integrating over the space of all fields, all functions with these boundary conditions. Right? Of course, the propagator, as we discussed, you just follow the prescription. You end up with a path integral over the phase space, right? In this case, it would be path integral. Sorry, I keep switching this notation and this notation. They both mean path integrals, right? I think this is my notation. This is my attempt last time to switch notation, but no work. So you path integrate over the phase space with some initial conditions on Ti and Tf, right? Yeah, and then the weight in the phase space will be basically the Hamiltonian, right? Which is pi phi dot minus. This is a Legendre transform of the action. We said that as was in the case of quantum mechanics, 0 plus 1 QFT, Hamiltonian, if the Hamiltonian is just a Gaussian kinetic piece plus a potential which is only space dependent or field dependent, you could perform the path integral over pi explicitly, the conjugate variables explicitly, and you end up with the path integral over the this picture. So this picture really comes about after you perform your path integral over canonical fields variable on the conjugate moment. Good. So the analogy is also straightforward. Let me remind you of another thing, frame dependence we talked about, right? So X and P, well, yeah, let me say it. So X and P were coordinates in the phase space. We're talking quantum mechanics. Of course, you could perform a rotation here in the phase space and pick different X and P's, right? That is frame dependence, right? Picking that's a choice of frame to describe it. Similarly, it doesn't matter because we're performing path integral over these guys, right? These are dummy variables in the interval. Similarly, the field phi's and pi's, the field and its conjugate momentum, are really, think of them as coordinates on the phase space, right? So there is some freedom, there's a frame that you've picked every time we talk about some representation, right? The representation is a frame. And you path integrate over the field, so we could arbitrarily field redefine the field. Good. Are there any questions? All right, the way we quantize this was, we said that an elegant way of doing this is using the generating functional, which is the path integral, with this extra source inserted, right? E to the power of I dx j x by x. Now my dx is over space time, so hopefully that the notation is clear. The free action after an integration by parts is this for massive scalar field. I already put the I epsilon in anticipation for Feynman propagator, right? To make the Fourier transform in time convergent. Is that good? All right. So we just, all that we needed to do to perform this path integral was to complete the square. And once you complete the square, you figure out, you find that the Feynman propagator, which is the inverse of this guy. The Feynman propagator is just the inverse of this differential operator, right? Appears here. That's what you need to complete the square. Hopefully you remember that. And once you complete the square, you get the z naught 0, which is the overall normalization in the absence of the source and the dependence on the sources of this form. The physics is in z0 j over z0 0. That's where the physics is, right? To calculate endpoint functions, which naturally come out by taking functional derivatives of the generating functional in the following way. You get time ordered guys. Oh, sorry, I should have said this. So you said j equals 0 after you're doing this. One important thing. This is, let me see if you guys remember or have seen this. Sometimes when we talk about partition, well, in statistical physics, hopefully remember, when you talk about partition function, right? When you take derivatives of the partition function with respect to beta, right? Or you get correlators, right? That's how you do correlators. Or let me talk about the generating function, right? I could take derivatives with respect to this in this way, z of j. Well, actually, I can put this to 0, right? J equals 0. Here is jx1 del jxn. I should have appropriate number of i's, I to the power of blah, blah, blah. What is this? We saw that this is the correlator, the time order correlator, right? Time order phi x1. Right? This can have connected pieces. Maybe that's too quick. Do you know what a connected correlator is? So 2-point function. X1, phi, X2. What do I get if I separate these guys by a large amount? There was a principle that there was an expectation. What was it? Right? Exponential decay in the limit of it going to infinity. No, sorry, what? This doesn't exponential decay. What happens if I take the limit of, by translation invariance, let's set this like this. This is space like 7. What happens if I take the limit of x going to infinity? What you obtain is that the correlator clusters, right? The correlator clusters. So the amount of correlations is not in the 2-point function, but it's in the connected 2-point function. Connected is right-hand side minus, sorry, left-hand side minus the right-hand side. But this is the connected. So if you ask yourself, what was going on in our calculation? Well, in our calculation, if you remember, the 1-point functions are all vanishing by Z2 symmetry. So the connected 2-point function and non-connected 2-point function are the same thing for free fields, right? Because of the Z2 symmetry, but it doesn't have to be. The thing that decays exponentially fast in the presence of masses in space is the connected correlate. The connected correlate is a measure of correlations, right? So this calculates the time order correlator, not the connected correlator, right? Good, everybody's with me? There is a brilliant trick to directly calculate the connected correlate. As you go to higher point functions, the connected correlate is more complicated, right? What is that brilliant technique? Take the log of zj. This has a name. What is this called? What is log of the partition function called? With a minus sign or something. Free energy. What's the point of free energy? Why do you talk about free energy? All right. What is nice about free energy? So as you can see, this guy is a generating function. Also, by taking derivatives of the partition function and generate the correlate. What is nice about the free energy is that if you take derivatives of free energy, you automatically get the connected correlators. That's diagrammatics of Gaussians. That's diagrammatics of field theory. Similarly, if you take the log of this has a name with an I here. This is called effective action. If you take derivatives of this guy, you automatically are going to get the connected correlators. We'll get there. We'll talk about that, but I wanted you guys to have heard this. I might actually find it as a homework problem. It's usually in most texts. All right. Good. So, for example, we saw that the 1 point function, well, here's the generating functional. Where was it? Oh, this one. Oops. So all I need to do if I want to calculate the correlation functions, tell me what the correlators are. What's the 1 point function? I have to take a derivative with respect to j, right? And set j equals 0. Taking a derivative with respect to j will bring down 1j and 1 factor of propagator, right? But I have to set j equals 0, so the 1 point function vanishes. Taking 2 point function, two derivatives will just bring down 1 Feynman propagator, right? That's the 2 point function. Taking 3, again, brings down a bunch of terms with odd number of j's. So when you set j equals 0, they all vanish. All the odd point correlators vanish. All the even point correlators, they will end up satisfying Wick's theorem. So for example, let's talk about 4 point function. The 4 point function will be basically these 3 pairings of propagators. So is that clear what I'm saying? So I think we wrote this last time, but let me just write it explicitly. Oh, I just erased it. Whoops. For those of you guys who are online, I don't know if nobody's online. So I'm doing derivatives of zj 1 over z0 0. Well, 0. All of this is 0 because it's free, right? Free field theory. That's what I mean with 0. Delta jx1. Delta. All of these have an I. jx4. This is phi x1 to phi x4. What is this? This ends up being I delta x. So there are 4 point functions for x1, x2, x3, x4. Right? What it ends up being is roughly cartoon is this. A particle from point x1 propagates to x3, and a particle from x2 propagates to x4. So 2 propagators, right? So that would be x1 minus x3, x2 minus x4. There's another term, if you take derivatives, there is this term. 1 goes to 4, 2 goes to 3. Because all I have is a propagator, everything is Gaussian, right? All the possible contractions. So this would be equal to 4. What's the other term? There's also this term. Right? All 3.
That's just multiplication of the like regular multiplication of propagators.
It's a differential law. Yeah. Because- yeah.
But there are distributions, right?
Like,
Uh,
why isn't the one that we don't get multiplied by like a common function?
Sorry. I don't understand.
These are
Like when you take the derivative of b like e to the ax, like you'll get like a to the ax, and then the next one will be like
Do this derivatives.
okay.
This is how you come up.
but you have
Let me ask a question. What is a propagator? Is it a function?
it's a Green's function.
Yeah, it's a green function. But what is special about it? First of all, it's a bilocal, right? So it's a bilocal. What else is special about it? So in this case, the bilocal is translation invariant, so it's only a function of one variable, which is the distance. How does it behave when the 2 points sit on top of each other?
It's symmetry.
Yeah, it's pretty similar. So it's not a regular function, it's a distribution. So these are multiplication distributions. So what does it mean for us, right? What you observe is not this 2-point function. What you observe, we talked about this before, is the observables are things like this for smooth enough functions. This is the kernel for the integrals you would need to do, right? If you wanted to calculate the time order correlator of function f1, f2, f3, f4 for these guys, this is the kernel. You have to integrate this kernel, this distribution against that.
With this meeting functions and this meeting functions can be.
It's a choice of your observable. Okay? But this is the generating functional. It contains everything you ever want to know, right? All right, is that good? So there's an elegant way of separating the connected piece. What we normal order, what is the vacuum expectation value of a normal order operator? 0, because we have moved all the a's to the right. That's the very definition of it, right? So which means that whatever the time ordered operator minus the normal ordered is the vacuum expectation value, right? So normal order, if you want a slogan for it, is 1-point function removed. Normal order operator O, and free field theory, of course, is removes the 1-point vacuum expectation value. Well, this is the rigorous statement. Maybe I shouldn't say it that way. I think that could be misleading. This is the rigorous statement, right? The 2-point function. Okay, so what I said is what I should say for 2-point. For 2-point function, that's what it is. For higher point functions, the Wick's theorem is the way to view it. Good. Is it clear what it's doing? Field phi has A and A daggers. You're multiplying these guys, right? And then you end up with all sorts of A dagger, A's, A daggers. Some of them contribute. The ones that have A's to the right don't contribute, right? So it's just repackaging everything in the language of A and A daggers. All right, so that's what we went over last time. Now, this slide is it's only one slide. Okay, this slide is very, very important. The way we go about one way, in my opinion, the most elegant way of going about constructing interactive or making sense of interacting field theory in a calculational way is through the so-called Schrödinger-Dyson equation. I already explained what Schrödinger-Dyson is in a sense. High-level words, your path integrating over fields, it's a consequence of the fact that fields are done by this. Right? So what is the expression? It says the following. It says, this is what it is. We derived this, right? Do you remember how we derived this equation? How do we derive this equation? No. So this is integral of d of phi. How do I write this down? I think I need a minus sign somewhere. I'm seeing a minus sign. Yeah, I think there's a minus sign here or somewhere. This is del phi of the power minus f h phi f of phi. What is this? What's this expression I wrote down here? What is the fundamental theorem of calculus? Tell me what anyone say what the fundamental theorem of calculus is. Forget about that. What's the fundamental theorem of calculus?
Like the derivative of an
Integral of a derivative, right, is the boundary value subtracted. If I'm integrating over everywhere and the boundary value goes to 0, this is 0 by the virtue of the fact that x is a dummy variable. The integrating over x. Similarly, del phi of anything 0. These are integrals after all. We said that we're not taking boundaries, right? We're pushing everything. All right, so what's in there? Let's put e to minus s phi over h bar. That's your action. Then put here whatever you want, some differential operator, some function, right? Now you get two terms, and if you could rearrange them in the following way, right? This is what that equation is. It's called Schrödinger-Dyson. When did we talk about Schrödinger-Dyson? Do you remember what the context was? I was trying to tell you what would be the notion of quantum equation of motion, right? What is equation of motion? Del S del phi, right? What is that operator that sits there? Del S del phi. All right, this is a master object in interacting theory or not. Take as f of phi your source. Good. So what do you obtain? You get del s del phi plus j of x is 0. This is what your equation is. Right? This is called the Schrödinger-Dyson equation. I don't need to set j equal 0. Let me pause and make sure everybody's on the same page. Here, when I take derivatives, to compare, I have to set all the phi's equal to del over del ij, I del j.
That's after you take the function derivative, yes?
This is the same equation I'm massaging, right? This is an equation that the generating functional satisfies. Everybody's with me on that. It could be used to define the generating function. Because if you have some object, z of j, that satisfies this, you could prove by taking derivatives of it, it will generate for you all the coordinates. That's what it is. This is called the Schrödinger-Dyson equation. It's just a consequence of the fact that z of j generating function is a path integral over the field, and field is a dummy variable. This is pretty much the only equation we have in quantum field theory. If we could solve this equation explicitly, you would have solved quantum field theory non-perturbatively. Of course, we cannot unless the theory is Gaussian, because the Gaussian case we solved this explicitly, right? We just did, right? What was z of j? It's just what was z of j? It was z of 0, e to minus a double integral of jj with a propagator. That's what we solved. In an interacting theory, good luck solving for this. However, what is neat about this is that when we set up perturbation theory, this is actually what's going to organize our perturbation theory order by order. Well, that's where Feynman diagrams come from. Yeah.
In case f of phi is just the interacting term, higher order terms in the field.
No, but S of phi is not Gaussian. S of phi is the
Yeah, no, but in the interacting case, f
In
of
the-
phi is just
F of phi is still the source,
okay.
right? But your S is different. Why? Because like, what is del S del phi? It has to be the interacting equation of motion. It's this that has the coupling in it. Right? The equation of motion has a potential term. We'll see that. That will be next week. Right? But I just wanted to point this out. These formal manipulations at this level, they're totally fine. Like they don't assume any, they don't make any assumptions. So the approach I'm following in this course is there are many different ways of deriving Feynman perturbation theory. But we're gonna take this as the approach. It's equivalent. I like this approach. It's very true to the, it's very easy to see where everything is coming from. And in principle, it's fully non-perturbative. That's what Schrödinger-Dyson equation is. I'll tell you later a little bit more about this. But what does Schrödinger-Dyson say for the free theory? Okay, think about that. Huh? No. Yeah, think about if you just somebody gave you this equation and said you have a free theory, what does that imply about Z of J? Well, look at this equation. What is this equation? This is your equation of motion. When they say they have a free theory, it means that pick your field, put the equation of motion of the free field here, right? And then every time you have a phi, you have to replace it with J. Yeah, think about it a little bit more. All right, so I'm going to switch gears. Until the end of this lecture, we're going to talk about fermions, right? So this was free boson, this was a summary of it, and I ended up showing your Dyson because I also wanted to have a slide or two about fermions and Schrödinger Dyson fermions. And then we're going to do the whole interaction theory, perturbative Feynman diagrams, using Schrödinger Dyson. All right? All right. So we talked about, as usual, I'm going to go back to basics. When we talked about free bosonic theory, we said what we ended up with was a collection of simple harmonic oscillators, bosonic simple harmonic oscillators. When we talked about the Dirac field, we ended up with a collection of simple fermionic harmonic oscillators, right? Good. What I'm going to do is, then we derive the path integral formulation in quantum mechanics and quantum field theory. I'm going to do another path integral derivation of simple harmonic oscillator, bosonic and fermionic. Right? This should be very, very easy to make sense of. That's going to be very convenient for fermionic fields. Right? So the conversation is going to be very basic in a sense, but it's sort of deep. So let me say the inverse first. What did we do to derive the path integrals? Why did we end up with a path integral and on the phase space? We had the propagator, e to the power minus IHT. We split it into many pieces. And then we inserted resolution of identity in the Q basis and the P basis. That's what we did. At each time, we did a resolution of identity on the phase space. Right? Okay. Good. Forget about the slides. I'm going to explain something very simple on the board, which It took me many years to understand this. So what's the simple harmonic oscillator? X and P, this is classical physics, right? So there's a phase space, it's two-dimensional, X and P. Right? There's some motion here. What's your Hamiltonian? Let me write it this way. What's your Hamiltonian? Right? Let me eat the frequency in space. What is this surface? This is a surface, right? Fixed Hamiltonian, fixed energy is some oval shaped thing. Right? Let me eat this into X so that I'm talking about round surface. Right? A particle with fixed energy is confined on this surface. What can it do? What kind of dynamics on the phase space can you imagine for it? Going either this way or going that way. Right? So, very good. How do I describe this? Going this way or that way? Let me define. This is now rescaled X, right? Omega is 1. Let me define this complex variable, Z. Right? So Z, norm of Z is my energy. This is classical. Right? And dynamics is Z going to Z e to the power of I omega t. And of course, Z star is going to Z star e to minus I omega t. That's your dynamics. We saw classical also, right? So the particles can be going this way depending on their energies. Everything goes around. In quantum mechanics, what happens is this. Z goes to annihilation operator. Z star goes to creation operator. Your Hamiltonian is still ZZ bar, so it's A dagger A. We'll normalize it up to a shift. What happens to your surface of constant energy? They become quantized. Your particle cannot sit at any arbitrary radius. There is a one allowed thing here, and there is another allowed thing here. The radius energy, right, is quantized. So they can only sit on these things. These are different energies. Okay. But energies are discrete. So in a sense, if you view the phase, if you think of quantization of simple harmonic oscillator as on the phase space, only certain circles are around. Is the dynamics actually the same? Is the dynamics analog of this? Yes. Time evolution of annihilation operator is e to the power of I omega. And A dagger goes 0. So quantum mechanically, all you're describing is that, well, now there's quantization. Things are going in circles, but like that. Right? These are only allowed values. Good. What are classical observables? Classical observables are functions of the phase space, right? So they are f of x and p. For example, x is an observable classically, or x squared is an observable, or xp is an observable, because you can observe it. So there are smooth functions on the phase space that I'm going to conveniently write as functions z and z star. What are quantum observables? As quantization would be a map from, let me call this A, that's my notation. It would be the following thing. It would be sending, well, actually, let me call it F. This is quantization. You would associate to every classical observable a quantum observable, which is like A and A dagger. But you have to be careful because if it's an observable, it has to be self-adjoint. So the order comes into play and it's complicated. Luckily for this case, there's normal ordering that takes care of everything. Right? That's what quantization is. Geometric quantization. Doesn't matter. Those words don't matter. This is what it is. All right. Everyone's with me? Very good. So now we pick up. remember this, okay? We'll come back to this. What is a coherent state in quantum in simple harmonic oscillators? E to the power of z a dagger, right? Acting on the vacuum. Ket z. An arbitrary wave function could be expanded in the z basis. This is an so coherent states provide an overcomplete basis, right? Z and z prime is e to the power of z star z prime. Good. So psi, the bracket of psi and z is just this guy.
I'm not sure if I understand what overcomplete is.
Means that basis means that if you take all of these linear combination of them, an arbitrary vector will be formed. Overcomplete means that you're not orthogonal. Like, yeah. This is what overcomplete is. If it were complete, it would be delta z prime. Complete would be like the number of generators would be the dimensionality of space, right? This is over. Yeah, but it's not complete. Is it obvious? Isn't it obvious that it has to be over complete? Exactly. Right? The Hilbert space is infinite dimensional, but countably, this is continuous, right? So ket z's are the closest it comes to classical physics. In classical physics, you see, so in the quantization, these are discrete. So the Hilbert space is infinite dimensional, but countably infinite. These ket z's are labeled like continuous variable. They're still describing things in phase space, right? But they act very classical. So what do they look like? The same way that I said I can map my observables this way, right? I can take a function, a ket. Yeah, sorry. You could think of a state psi in this basis as this function. Good. What we're going to do, let me just tell you in advance. Before, what we're doing to get our path integral, we're inserting resolution of identity in the x and p's. We're going to now do resolution of identity in this overcomplete basis. What is the resolution of identity? It's this operation. So this is a coherent state approach to path. It's equivalent. It's equivalent. Turns out to be more convenient for fermions. So this is a resolution of identity. Hopefully it's clear why I have a minus z squared here. No? Because of this guy, right? All right, this is maybe if it's not clear, check that this is a resolution of identity. All right, very good. So if you have a function a of z star and z prime, oh, yeah, sorry. If you have an observable a dagger a, its matrix elements like this is a of z star z prime e to the power of z star z prime. This is just an identity. Good. Let me pause here. This picture I think is useful to have in mind. Just keep that in mind. Are there any questions about this? So all we are doing is that we are viewing everything in the phase space basis, coherent state basis, in which when you evaluate the a dagger goes to z star and a goes to z, right? As you can see, if you have normal order, of course, there's normal order. In principle, in general, there's a problem with quantization, which is given a classical observable in the phase space, there's no way of constructing an operator in the Hilbert space uniquely. Why? Because the order matters. In free field theory, we're in this free, simple harmonic oscillator is free. We're in this nice setup where you could canonically fix the order. And that's what this normal ordering does for you. All right. So to derive the path integral, what we're gonna do is we're gonna start with the propagator. And of course, take the Hamiltonian and write it. Previously, we wrote it in terms of Q hat and P hat. Now we're gonna review it as a dagger function of a dagger and a, right? We're gonna expand it as before, right? Now we're gonna insert resolution of identity in this over complete coherent bases like this. Previously, what I was doing, if you remember, was I was inserting Q hats resolution of identity and P hats resolution of identity, right? Here I'm just doing the Z's. And then I have to path integrate over Z and Z star with this weight. It's coming from the resolution of identity. All right. Anyway, so I can trust you guys can follow these 3 lines of algebra, and you absolutely should. The end result, you just follow exactly what we were doing before, is that you end up rewriting this propagator as a path integral over Z and Z star, integral of an action, which is Z dot star Z. There's a minus I over 2 plus I over 2 Z star Z dot minus H of Z star Z. There is this extra bit that appears. This depends on the initial and final state. Initial and final states, and these are the phases. So you could identify this as the action. Is this the action that is this an action you recognize? What is this? You still have this expression on the board. X plus IP. Plug it in there for Z. See what you get. Recognize the expression. So after the dust settles, this is what you end up with, right? So it's a path integral over in the coherent basis, right? Coherent state basis. That's an alternative. Who's with me? Right. Next, I'm gonna say this for the very, very simple setup of a qubit, aka fermionic, simple fermionic quantum oscillator, right? So what is if you remember, the algebra was C and C dagger. What was the algebra? The anti-commutator CC dagger is 1. It's 2-dimensional Hilbert space. You have the coherent fermionic coherent states like this, and their expansion is 1 minus sigma C dagger 0. Why just this? Yeah, because these are anti-commuting. Right? It's 2-dimensional. Now, we saw before that a spinner is basically a collection of these fermionic harmonic oscillators. So, well, let's just do one for now. You have the Xi and Xi bar, right? This is the analog of Z and Z star. I'm just writing this way. So you have the coherent states. I'm already writing a collection of them. And they satisfy the following properties. That C acting on one of these states gives you this. What is the analog of this in the bosonic case? This is a fermionic coherent state. What does this equation mean? They are the fermionic coherent state is the eigenvector of fermionic annihilation operator. The bosonic coherent state, one definition of it is that it's the eigenvector of the annihilation, bosonic annihilation operator. Right? And they, of course, satisfy the following relation. This is it's an overcomplete basis. You recognize this, right? This is a z star z prime thing. There's this nice relation of derivatives that holds for all coherent states, bosonic or not. All right, these are Grassmann variables. Good. Here's your resolution of identity. It goes through nicely as before. Your propagator, you write as a path integral this way, and their action is psi bar psi dot I over 2 minus I over 2 psi bar dot psi minus h of psi bar psi. Does this sound familiar? When we talked about spinors, the Dirac action we wrote was first order, right? It looked like this. All right, what's the is that good? Right? So for bosons, we ended up with the path integral in the phase space, x and p. We could do the path integral on p explicitly, right? Here, psi and psi bar, you can't do that. This is the action, and you have to deal with it. Well, actually, you could do the path integral explicitly if the theory is free. But if the theory is not free, you cannot do it. We're going to do it when it's free. All right. So what we're going to do is we're going to calculate the generating functional by introducing sources for the Grassmann variable, Grassmann valued fields. Here's your 2 endpoint function, which is the time ordered a bunch of psis and a bunch of psi bars. Right? We already know that it should be totally antisymmetric. It should have this property. It will come out. All right. So you have 2 dynamical fields, psi and psi bar. This is still, in a sense, the path integral of fermions always remains in the level of the phase space. So you introduce a source for psi and introduce a source for psi bar. The source for this guy is eta. The source for this guy is eta bar. Pay attention to the way, what order I write things. If you take derivatives with respect to eta and eta bar, they bring down and construct this object. So this will be a homework problem. All right. Very, very crucial. Be careful with the sign. This order is important. With fermions, you must be very, very careful with signs. When you take derivatives of z with respect to c bar, eta bar, which is the source for psi, you bring a psi to the left. When you take a derivative with respect to eta, you bring down a psi bar to the left with a minus sign. You'll have to keep track of these. And when you do 2 derivatives with respect to eta and eta bar, this is what you update. If you, after taking 2 derivatives, just take eta equal eta 0, eta bar equals 0, you get the 2-point function, aka propagator, right?
If we did the integration,
What do you get?
same or
Good question. Do it. You will get the same up to a minus sign. That's obvious, right? So you're asking whether is a minus sign or not. I'll leave it to you guys to figure out. but it's not obvious. Okay. All right. All right. Maybe it's important you do it. It's important you do it. All right. Let me pause here. Good. So what did we say so far? We talked about how you could do the path integral in the basis of coherent states. And that is the fermionic path integral we're going to be doing. And yeah, we are after generating functional. We have to path integrate over psi and psi bar. Right? Do you remember what they're called? Psi and psi bar. Psi is a particle. Psi bar is relative to an anti-particle. Right? Why didn't we need to worry about this for scalar field? This is on anti-particle. What did we need to worry about this for the complex scalar field?
Yes.
Yes. Because we had phi, and the canonical conjugate to it was phi dagger, and the action was not phi dagger squared over something that it could perform the path integral over. For the complex case, there's particle and antiparticle, and there's a source for each of them, similar to fermions. So if there was a question before about particle and antiparticle, why are they here? Why were we talking about charge symmetry, charge transformations, C transformations? This is the origin of it.
But in the complex scalar, we didn't have to worry about Grassmann and Newton.
No, not at all. Yeah. All right. So let me see. Let me pause for questions. Are there questions? What I want to say in the remaining 15 minutes is we're going to derive the propagator or the generating functional for free fermions. Good. Do you have a guess without looking over there? Is it over there? Maybe it's not. Oh, it is over there. Do you have a guess as what the answer is going to be? What's the answer? What was the answer in the case of bosons? What was the propagator for the boson?
The inverse of the Klein-Gordon.
It was the Green's function for Klein-Gordon operator. So it was the Klein-Gordon inverse of Klein-Gordon, right? In momentum and Fourier transform in space and time, it was just 1 over the on-shell condition, and we had to shift it by I epsilon for the convergence of the correlator, and that actually led to the time order, right? So what would be the analogous thing? The propagator would be the Green's function for what equation? Dirac equation. So it would look like the inverse of the Dirac operator, right? In Fourier transform in space and time, and you would probably have to do a shift, right? Okay. Good. When we did the looked at the propagator for free scalar field, what was it in the momentum and energy basis and space and fully Fourier transform form?
1 over p squared.
Right. So it had 2 poles, right? One of them was omega k, the other one was minus omega k. One of them is particle, the other one is antiparticle, right? Here, can you tell how we're going to get the particle and antiparticle?
From the fact, I think, because if you invert the Dirac operator, you just get I1 over p slash minus m. But you can bring it into like complete the square and then
There's another way of saying it. That's a mathematical trick that's valid. There's another way of saying that. In the case of fermions, you don't have one field. You have a pair of fields, psi and psi bar, right? So how do you find equations of motion, or like classical equations of motion? You have to vary the action with respect to psi. You have to vary the action with psi bar. There are 2 equations. There are 2 propagators associated with them. One of them is the particle, the other one is antiparticle. And the poles are exactly, well, they have a nice structure that you expect, right? All right, so here's the Dirac equation, Dirac operator. and I'm already using the Schrödinger-Dyson equation, right? Is it clear that this is the Schrödinger-Dyson? What do you remember what this is? Let me write this on the board in case. Let me write down the equation, the Schrödinger-Dyson for scalar field, so that you can compare properly. So Schrödinger-Dyson for scalar field was something that satisfied this equation. Was this equation, right? What was here?
Or the Lagrange.
Del S del phi. There was ij or something here, and then this too. This I have to evaluate at phi. Don't mind my eyes, right? So what do we have here? We have the action. If I want the equation of motion for field psi, I have to take functional derivative respect to psi bar, right? And I have to set this. I use a different notation. Okay, psi equal I del. What did you call it? Bar? Yeah, bar. Plus I. What is that? What do you call it? Z? Yeah. Z of eta bar equals 0. There's one equation for this and there's one for psi. For psi bar, sorry. Good. Here's our path integral. After integration by parts, basically what you have is this is the Dirac operator, right? And here are the sources. Notice the order. So we're talking about the Dirac operator. So this guy is a 4x4 matrix. So one way of writing is I gamma mu del mu minus m identity, right? This is in the representation through Lorentz group, right? So now I'm jumping to 3 plus 1 dimensions. So whatever the hell S is, propagator is, its inverse is this. Good. If you want to complete the square, what you need to do is this is psi bar S minus psi plus eta bar psi plus psi bar eta. The way you complete the square is by writing it this way, by the following shift. Now, this part of it, so this is a Fielder definition, call this psi prime, and this is psi bar prime. This is just a Gaussian integral. It will give you that psi zero, z zeros. This is the leftover. So previously we found what? What was our propagator? What was our, we found for the scalar field, we found z of j was z of 0 e to the power of integral jx, jy, I. Yes. What do you find here? Z of eta bar, z of 0, 0, integral of, I think eta bar, right? This is, I call it S, right?
But S or S?
S.
I mean, S.
S, this term.
Okay.
This is, I completed the square. This part will contribute to this. Z 0, 0. This is the leftover.
So not the inverse of the differential.
S is the propagator.
No, you put S inverse.
Oh, no. Yes.
S is the propagator. S is the inverse of this guy. Right? Good. I have a lot of typos, but this is not one of them. All right, so this is what my z becomes, right? Minus I integral of d4 eta bar s of x y eta x. Hopefully it's clear that these are 4-dimensional vectors. This is a 4x4 matrix, right? S, x, y is the Green's function for this operator, the Dirac operator. Now comes the comment that was made earlier. Oh. Right. I wanted to do it with different order, opposite order. But if delta of fx minus y, think of this as minus, thing as plus, okay? So delta of x minus y is satisfying this equation. If I act further with this operator, I can, not much changes. And this is an identity that this guy is just a Klein-Gordon equation. This tells you that there are various ways of writing the propagator for a single fermion. You could write it as the inverse like this, or you could write it with the plus above and the Klein-Gordon propagator down there. We're going to be using this trick over and over again. We almost always use this form. This sort of makes sense, right? Why does it make sense? Because we don't want to working with inverse of 4x4 matrices, right? We want to work with the matrix 4x4. It's easier to work with the matrix itself. This is the point of this, right? Writing the propagator as this 4x4 matrix divided by this. This is proportional to identity. This is so when I write this down, it means that this differential operator multiplied by this differential operator is a Klein-Gordon operator multiplied by identity, right? So identity inverse, I know what the hell it is, and this is why we're writing it this way. We'll be using this form a lot. So what is the on-shell condition for massive scalar field? It's this thing, right? With I epsilon. Right, let me write this as p squared.
It's minus m squared.
Whatever. Yeah, sure. Okay. Good. So here, what I should be dealing with is something that looks like gamma mu, p mu, minus I m, or there's an I here, right? Plus I epsilon. These are matrices. These are gamma matrices. So what we write down looks something like this. This is a 4x4 matrix divided by. Okay, we're going to be using this expression over and over again. As I said, it's because it's easy to multiply matrices, but the inverse of them is just an easy way to keep track of things. All right, so let's write down the matrix explicitly. Here it is. As you can see, I already I don't know what signature I'm picking, but it's minus k squared minus m squared. This was my signature. Sorry about that. So anyway, gamma mu is, if you remember, sigma mu here, sigma bar mu here. Good. Okay, so just plug them in. If this is your S of f, is I over minus k squared minus m squared plus I epsilon multiplied by this 4x4 matrix. This is plus m, and this is gamma mu k mu, right? So all I did was I wrote this down. Well, k mu. This is what the matrix is. How about this antiparticle? What was the charge transformation? It was swapping sigma and sigma bar, right? So you know the propagator for the other one. All right, so I'm going to pause here for questions, and then I'll have a little summary.
If you were to do this in canonical quantization,
we did this in canonical quantization.
What's that?
We did this in canonical quantization.
The fermion field propagator.
Yeah. We calculate the 2-point function.
Okay.
But go ahead, but
Yeah, no, yes, the procedure is quite easier with path integral.
the path integral for the free fields is not that different for free fields, but in fractions. The reason is the reason is showing your dice. Or dice. Very similar. He didn't have a PhD, so you guys are ahead of him. Huh? Not yet. That's a good point. Well, I think you're gonna. Well, he's not making progress in that direction. Let's leave it at that. All right. In summary, what did we do? We quantized fermions using path integrals. The natural way to do it was on the phase space. We can simplify it further as opposed to scalar field where it was a p-squared piece that we could explicitly path integrate over. And what we so the most natural thing to do was, the easy thing to do was to do it using coherent basis. This is in no way essential. You could use your way of writing the path, right? But I wanted you to see this formulation as well. I erased. I love this picture of phase space. Z and Z bar going to Z and Z star going to A and A dagger. Some brainwashing me with this. This is the path integral, right? And there are sources for psi and psi bar. As a matter of fact, if you had a scalar field, I said that before, right? But if you had a scalar field, well, where the action was not p squared plus x squared plus v of x, but it was p squared plus x squared plus v of x and p, it was not possible, wouldn't have been possible to perform the path integral over p. You had to stay on the phase space, right? And then in that case, the analysis would be more convenient if you use the coherent basis. It would be more convenient to use it. All right, so here's our path integral, and we talked all about this. Like I think there's not much else to say for the free fermion case. The Klein-Gordon, not Klein-Gordon. The Dirac equation is this. You remember that this is a 4x4 matrix. These are Grassmann valued sources, and once you path integrate, you obtain this. It's Gaussian. All right, I want all the way up to here. So fermion propagator in real space looks like this. In a momentum space, it looks like this. K slash is K mu gamma, right? These are the expressions that you should absolutely remember always.
That I in front of the propagators is it that essential?
Yes.
Why is it?
Why? Huh?
It takes care of the Euclidean to be considered.
Well, it's a signature of the metric.
Oh,
It's very essential.
so there are weak rotation disappears.
It has to do with unitarity of representation.
Okay.
Yeah, of course. Right, let me try to make a couple of comments. Something very important about this is the following. So now you have two types of particles in a sense, particle and antiparticle, right? Previously, the Feynman diagrams we're finding looked like this, right? So this was a time order 2-point function for a scalar source. Sorry. So of J for scalar field over Z0 is e to the power of minus half integral of, now, let's minus half J. You know this, right? So 2.5. What is it for the free fermion? If I had a red marker, I just wanted to circle around it. Theta bar. What does that mean?
Particle gets annihilated by another particle.
It means that the correlators that are non-vanishing for the free fields should have a number. Exactly. If there's a this is a particle and then this is the antiparticle. They should have zero charge. Charge was the number of particles minus the number of antiparticles. These are vacuum fluctuations, right? So if you have a correlator, if somebody wrote this, like, I don't know, like psi x1, 5, psi bar of y1, y16 bar, you know that this is 0. But as a quantum fluctuation, it's impossible because it's not right? It's charge. So you see the role of charge. That was my last comment. Yeah, thank you.
We chose the